I also wanted to compare experimental probability to theoretical probability using a dice roll simulation. So usually we get the class to perform this experiment of rolling 2 dice several times, recording this sum. So we calculated in the lesson what the probability was to roll a sum of 7, because we said that was the most likely roll to occur, because it had the most ways to actually get a sum of 7. If you guys have played a lot of dice games, especially Settlers of Catan, you know that the numbers that are closer to 7 have more likely probability, and the farther away you get from 7, the less likely something is, right? If we're looking at a sum of 2 or 12, there's only one way for that to occur. For a sum of 2, you have to get a 1 and a 1. For a sum of 12, you have to get double sixes, right? So we should see, based on a graph of the probability, we should see a peak in the center at 7, and then we should see it kind of fade off and get smaller. Now this should technically be a bar graph. There should be spaces in between because this is discrete data, but I need to use this simulation in order to show lots of trials. So we're going to make do with the fact that they've connected the bars, and we're going to pretend for a sec. If I do the experiment that I usually do in class and get 10 rolls, let's take a peek. So we say 10 rolls, this is what happens. The 7 did occur most often, but it tied with the 11. 11 shouldn't be very likely, so that's kind of weird. Let's take a look at what happened with student B. Let's take a look and see what Foy's roll was. So if we reset, roll the dice 10 times. So Foy noticed that she got a sum of 7 3 times, so again, that's high. And a sum of 4 comes in second. 5 and 10 never happened, that's kind of interesting. Okay, let's take a look at another one. Let's take a look and see what Martin gets. So Martin rolls his 10 dice, and you can see that 5 actually occurred more times than 7. Oh, well, that's weird. All right, one more try. Let's take a look and see. Let's see what Avery gets. Rolls 10 dice. Avery gets a 7 3 times, and then the numbers closest to 7 happen in the next most often, but then no 9s, no 5s, and several 10s. So what we have here is we have a low number of trials, and we're seeing that they don't match the theoretical probability. This is what we call statistical fluctuation. It's because other outcomes are possible. They're less likely, but they're still possible. It doesn't mean they're not going to occur, even though you have a small number of trials. Okay, so what happens is we don't actually see the same experimental probability from each set of trials to the next, right? So Avery here saw 2 10s, but one of the other people didn't see any 10s. And what happens is they kind of end up sort of balancing themselves out if we put all of those trials together. So if I put all 40 of the trials I just did together, what we'll end up seeing is a little bit more balanced out. Now I can't do that exactly, but what I can do is then let's run 100 trials, see what happens. So this will be like all the data management classes rolling a pair of dice 10 times. And you can see here now that there is a peak kind of in the middle. 6 and 7 are occurring the most, and then 8. But you can see that 6 actually occurred more times than 7. So it's still not matching the theoretical probability, but we are seeing it getting a little bit closer. If I then get all the students to roll the dice 10 more times and we collect that data, we see this. Again, 6 is still happening more than 7, so that's kind of interesting. And we have this 3 happening quite a few times, right? You can see 2 and 12 not happening very often. Let's try again. 100 more. Okay, again, we're starting to get a little more kind of constant kind of rise to the middle and then kind of a fall off, but it's not symmetric necessarily yet. You can see 5 isn't occurring all that often. 6 is still occurring more than 7. Let's increase this quite a few more times. So I'm just going to tap the 100 several times. So you can see total rolls up there just above the graph. So you can see now the 7 is actually winning out. It's happening the most times. The 10 just got slightly below the 9. Let's jump quite a bit here. Let's add 10,000 rolls. See, now we're fairly symmetric, right? 7 occurs most often. If I add another 10,000, a couple more, you can see we're really getting quite symmetric. The 2 and the 12 are happening least. 7 is the highest. So again, what this is called is statistical fluctuation. If you do a small number of trials, your experimental probability will not necessarily match your theoretical probability. Over the long run of conducting many, many trials, those kind of statistical errors will balance each other out. One person might get quite a few 10s, someone else might get quite a few 4s, that'll kind of balance out. Another group might get even more 7s than they were expecting, right? But over a series of a lot of trials, your experimental will approach your theoretical. Okay, Thanks.